Hi everyone. Okay, so we've talked about a second derivative in the context of a position, velocity, acceleration type problem. But we need to make sure that we build up some of the more general idea and notation. So that's what this chunk is. Okay, so we already have, let's see, what do we want to say here? Right, okay, so we're always thinking about starting with a function f. We decided in the last section that f prime was actually also a function that input the same x values as f and output its slopes. And if it's a function, sort of a reasonable next step would be to conclude that we should be able to take its derivative. So we're supposed to be able to take the derivatives of functions regardless of whether they mean y value as output or slope as output or whatever. So if you take the derivative of a derivative function, you get what's called a second derivative. And if you took another one, it would be a third derivative, and another would be a fourth, and so on. So our notation, the prime notation, is the easier one. Here's our f double prime. Just put two little apostrophes next to it. If you want to use the dy dx notation, so again, we're assuming that y is the same as f of x, y is the output of f of x, it ends up looking like this, d squared y over dx squared. And there's sort of like an implied parenthesis here. You don't have to write it, but that's the whole dx squared. And the reason it works out like that the d is squared and the dx is squared, is really what we're doing is y is the name of the function. So it's not showing up twice. We're taking the derivative, I wrote it here, but I think I want to do even more, of the derivative of y. So the d over dx part is the part that means derivative, and y is just telling you who to take the derivative of. So if you take a derivative and then another derivative, you've applied the d over dx twice, but there's still only a single y, and that's why it looks like that. The big thing is just for you to recognize this. If I give you an equation, y equals something, and I ask you for d squared y over dx squared, you should know I mean take the second derivative. The second derivative function tells us about the slopes of the first derivative function. So basically it's telling us how quickly the slopes of the original function are changing. So it's like the slopes of the slope function. So it's the rate of change of the rate of change of f. So it's telling us if the slopes are getting increasing or decreasing, or what's going on, and the end result of that is concavity, which we mentioned in the last problem as well, so which direction it's bending. Okay, so a little bit of other vocab tie-in here. We should have heard a lot of this, but I just want to make sure it's all on everyone's radar. Okay, so increasing and decreasing, I definitely hope everyone's known before we hit this section. Increasing means the y values get bigger as the x values get bigger. This should be happening whenever f prime is greater than 0. So positive first derivative means increasing. Negative first derivative should mean decreasing. Your y values are going to get smaller as your x's get bigger. We're now adding to that concave up and concave down, which you may or may not have run into before. So concave up and concave down, this is talking about whether your function has an upward bend or a downward bend. So I've written one way to think about this, but there are a few. A function is concave up if its slopes are getting bigger. So that's a different way to say this. If the slopes are getting bigger, it's concave up. And if the slopes are getting smaller, it's concave down. The one I actually put here is a really nice visual. If you look at the graph and you draw a tangent line, and everywhere nearby the point at which the line is tangent, everything on the curve lies above the tangent line, then it's concave up. So concave up functions bend up above the tangent line, and concave down functions bend down below the tangent line. So again, several different ways to think about concavity, but it all boils down to which direction you're bending. So with that in mind, oh, and also this tie-in, so concavity is related to a second derivative. If the second derivative is positive, you're talking about a function being concave up, and if it's negative, the function is concave down. Okay, so just to run through some of the possible combinations of increasing, decreasing, concave up, concave down, I want to look at these 4 pictures. These are kind of our basic combinations of those two that we can get. So if this is our function that we're looking at right here, here, let's see, I don't need the giant marker. Here, the function is increasing, which means the derivative is positive, but it's getting less steep as we go. So slopes are decreasing, which means it's positive concave down. And again, there's many ways to say concave down. So one is the slopes are decreasing. One is just knowing what this downward bend looks like. One is if you draw a tangent line, the curve would lie below the tangent line. All of those things are telling me concave down. So there's increasing concave down. This one is also increasing, but now it's getting steeper as we go. Slopes are getting bigger, so this is concave up. And again, you can say slopes are getting bigger, I see an upward bend, or I see that the function lies above its tangent line. All of those would say concave up. So we have increasing concave down, increasing concave up, and then this one is decreasing. Y values are getting smaller. I don't know why this one got an X. Okay, so let's see. This is usually one of the ones that gets a little tricky for people. These are negative slopes, but they're getting bigger, right? So if this is -2, maybe this is -1, and this is -1/2. Those are getting bigger. This is concave up. And this is one of those cases where you might want one of the other alternative ways to think about it, because people look at that and want to say slopes are getting smaller because it's getting less steep, but numerically the numbers are getting bigger, -2, -1, -1/2. So you could say you see the upward bend, or you could say it lies above a tangent line as well if you're having confusion with the bigger slopes and smaller slopes thing. This one is also decreasing, but this time, let's see, slopes are getting smaller. So this is concave down. So again, with the slopes getting smaller, if this was a slope like -1/2, then we'd hit -1 and -2, and those numbers are getting smaller. So it's not necessarily about steep or less steep when I say slopes are getting bigger or smaller. So this is decreasing concave up, and this is decreasing concave down. And again, you could draw in that tangent line, that totally missed, but pretend, and see that the graph would lie below the tangent line. Okay, one last little bit of vocab. This is kind of like the vocab video. Local max and local min are going to be really important for us later, and there's no reason not to talk about them now. They're very easy to spot on graphs. The thing that we'll work on later is, given an equation, can we use the derivative to help us algebraically find local maximums and minimums? So the definition of a local maximum is that you have a local maximum if the y value at that point, okay, so let's say this exactly how it shows up. You have a local max at x equals c if the y value at c is at least as big as all the nearby y values. And you have a local min at x equals c if the y value at c is at least as small as all the nearby y values. So local max and local min, I think I have a picture coming up in a later one, but just to show it, this would be, if this is the graph of your function, this would be a local max, and this would be a local min. So there are definitely bigger y values and smaller y values on the function, but if you kind of zoom in and look only nearby, that's smaller or bigger than everything nearby. Okay, and then very last one is, we've talked about concave up and concave down. So it's nice to talk about what the name for the point where that switches. So if you have a function that switches from concave up to concave down or vice versa, that's called an inflection point. And actually the graph I just drew, this one right here, would have an inflection point. And there's definitely some estimation here, but I see that this is all definitely bending downward. And then I see that this is all definitely bending upward, and somewhere in the middle, around there, but again, there is some estimation involved in that, there would be an inflection point. So in order to switch from concave down to concave up, the graph has to straighten out for at least an instant. Okay, thanks for watching.